Welcome to this NPTEL course on Advanced Pre-Stressed Concrete Design. We are in the module 10. In this lecture, we will focus on analysis and design of post-tension flat plate. Particularly, we will take a real case, a PT slab, and we will go through how do we do the preliminary design and the same time how do you arrive at the equivalent frame properties, and then we will also look at how our manual calculations using equivalent frame method is going to compare with that of commercially available software results. So, the expected learning outcomes are the student, after going through the video, shall be able to understand the preliminary design of post-tension slab, and then will be able to gain knowledge on the analysis of PT slab using equivalent frame method through an example, and will be able to appreciate and understand the differences between the results that you get from a finite element analysis model and then equivalent frame method. Okay. So, this is the example that what we are going to look at. You can see here is a floor plate. The floor plate have columns that are regularly spaced, and what we have in the x direction or in the east west direction, we have 5 spans and each one of them is 8 meters. Then in the north south direction, we have 3 spans and each span is about 9 meters. So, we are going to design for this layout. You can also see here that there is a lift core is there, right, and then you have a corridor area here, right, corridor area where higher live loads is assumed to be acting. Okay. And I have done the preliminary design and we have come up with a layout based on the architectural plan. Columns or typical columns are 500 millimeter by 500 millimeter, and the lift core wall is designed to be 250 millimeter. Now, with this arrangements, we are going to look at only the design of a post-tension slab. As you can see, this is a slab without any beams. So, the slabs are directly supporting on the columns, and the columns also they do not have any column capital at this point of time. So, we are going to design this post-tension slab for this particular layout. Okay, what are the material properties? The density of concrete can be taken as 25 kilonewton per meter cube. Compressive strength of concrete, I am assuming because it is a PT slab, we are going to take slightly higher grade for 40 megapascal, and yield strength for a non-pre-stressed steel. This is for non-pre-stressed steel. That means for regular deformed rebars, I am taking 415 megapascal. And strength of the pre-stressing steel or the grade of the pre-stressing steel, as usual we are taking 1860 megapascal, and you can see the initial stress, I should not say the effective pre-stress, what I am stretching is about 75% of its ultimate strength. So, I should also say this is as effective, I should say instead of effective I should say initial pre-stress, okay, FPI let us say, and effective pre-stress will be pre-stress after accounting for the losses, right. So, this is your initial pre-stress, and then the diameter of the pre-stressing steel is taken as half inch strand, which is 12.7 millimeter. And live load, because this is going to be an office building and we have 3 kilonewton per meter square, and on the corridor that we have seen just close to the elevator core, I have to take a slightly higher live load, which is taken as 5 kilonewton per meter square, and superimposed dead load, that is accounting for the floor finish and other loading, I am going to take it as 1.25 kilonewton per meter square, right. So, these are the information that are given to us. Okay. Now, the first thing when we come to the design of the slab is I have to find out what should be the thickness of the slab, and as you can see previously as per the Post Tensioning Institute manual, we have given some recommended values. So, for a typical L by D ratio for a continuous pre-stressed floor slab or a flat plate, we can take L by D as 45. So, the initial depth works out to be 200 millimeters. So, this is actually 200 millimeters seems to be sufficient as per this, but again we know that it is a flat plate, we have to check for the punching shear as well, right. So, for initial estimate based on the L by D or L by H, we can take it as 200 millimeter. Now, we should also make sure that the thickness of the slab is adequate enough from fire rating point of view. So, typically IS 456, it requires the thickness of the slab as 125 millimeter for a 2-hour fire rating, and we are providing 200 millimeter, which is greater than 125 millimeter. So, the thickness whatever we have initially chosen is good from fire requirement point of view. Now, we have to check for the punching shear. So, here we are just showing some initial calculations. We are taking a typical interior column, right, which is at B2, and these are your tributary area for this column. So, you go to the mid distance to the next column on the left and right side, similarly to the top and bottom, and this becomes your tributary area. So, whatever the load that is applied, that will go to this column as a shear, right, as an axial load plus the slab shear. So, we have to check for that. Okay. So, the tributary area is 8 meter by 9 meter for a B2 interior column, right, and then we can go ahead and look at the loads now. The self height of the slab for assumed 0.2 200 millimeter and multiplied by the unit weight, which is 25 into 0.2. So, that works out to be 5 kilonewton per meter square, and superimposed dead load is given as 1.25 kilonewton per meter square. Live load on the slab again is given as 3 kilonewton per meter square. So, as per IS codes, we take load factors as 1.5, which is slightly higher than what you have for ACA code, but we take 1.5. So, when you multiply with 1.5 and add up all these things, so you get a total factored load of 13.875 kilonewton per meter square. Now, what is the factored shear that it is acting? This WU multiplied by the tributary area, which we have taken that as 8 meter by 9 meter for an interior column. So, when you multiply that, I get a shear of 999 kilonewton, right. Now, we have to, this is the demand. Now, this is because we are talking about an interior column, right, interior column. We can also take one exterior column as well, okay, and then check for it. Okay. We are just showing it for one interior column. Now, in the interior column, again we have discussed it in the part 3 that there is also going to be an unbalanced moment that will be existing between the left side and right side of the column. That portion of it will be transferred through shear, and a portion of them will be transferred through bending in the slab. So, to account for this unbalanced moment transfer through shear, what we are going to do is the factored shear is multiplied by 21.2, or I am increasing it by 20%, which works out to be 1198.8 kilonewton. Now, if it is an exterior column, then this unbalanced moment, right, through shear will be high. So, what we do is then the VU is typically multiplied by 1.5, 50% we multiply, because the unbalanced moment is going to be higher than through shear, more demand will come. So, that is the reason we will multiply by 1.5, but here we are taking an interior column. So, we are just multiplying by only 1.2. Right. So, now that we have got this, and this is the critical perimeter, we have got the demand. Now, we have to check for the capacity. Now, again this is an interior column, and you know that critical perimeter is going to be C1 plus D by 2 plus D by 2, right. Similarly, on the other side it is going to be C2 plus D by 2 plus D by 2, right. So, this is a critical shear perimeter. Okay. Now, what is that? So, this is the area in one way shear, we know that it is the width of the slab multiplied by the effective depth is what it is resisting. But in two-way shear, that entire perimeter area is actually resisting that two-way shear, right. So, that is a punching shear. Now, I have to calculate the capacities using that. So, the B naught is nothing but the shear perimeter. In this case, it is going to be C1 plus D times 2 plus C2 plus D times 2, that is your shear perimeter. So, this is nothing but your shear perimeter. Okay, that is the B naught. So, the equations for punching shear is coming from Ks times tau c, which is the shear strength of the concrete, and there is a beneficial effect of a pre-stress which comes from 0.3 times FPC, whatever that pre-stress, concentric pre-stress, that value that is there, that we multiply by 0.3 to account for that beneficial effects of pre-stress. That entire thing we are multiplying by B naught into D. B naught is the shear perimeter and D is your effective depth. In addition to that, this is a vertical component. Always we have seen that the pre-stressing is going to produce horizontal component and a vertical component. Vertical component will directly nullify the load that it is coming on the slab. So, for now let us look at only, let us consider conservatively the vertical component of pre-stress is taken to be 0 conservatively, but if it is not meeting the norms, then we will go ahead and account for it. First, let us assume Vp to be 0 to be on the conservative side and check whether it is meeting the demand or not. If it is not, then we will go ahead and see how do we account for Vp, right. Now, tau c 0.25 into square root of FCK, and Ks factor is 0.5 plus beta c, but the entire thing has to be kept less than 1. So, and beta c is the ratio of short side to the long side of the column, because here it is a square column, then this ratio is 1. So, Ks will become 1.5, but it cannot be more than 1. So, I have to take it as 1. And Fp is the average pre-stressing force, and the typical value ranges from 1 to 1.5 megapascal for the entire width. Okay. So, depending upon how you lay out the tendons, this value can vary, but typically on an average sense it has to be between 1 to 2 megapascal, and B naught is the perimeter of the critical section, and D is the effective depth of the section, and Vp is the vertical component that we have talked about. Now, we are plugging in all the numbers. 0.25 into square root of 40 becomes 1.581, and effective depth is 160 millimeter, and B naught, as you know, you can see 500 is your column dimension plus effective depth is 160, and 4 times, because you have 4 perimeters, 4 sides. So, perimeter will be 4 times that. So, that you get to 2640 kilonewton. Vp again we are this because we are taking in a conservatively, right. So, when you plug in all these numbers, you get your Vc as 826.2 kilonewton, and you know the shear demand was close to 1200 kilonewton. So, the shear capacity is less than the shear demand. So, definitely the thickness what we have provided 200 millimeter is not adequate from punching shear point of view, right. So, hence the thickness of 200 millimeter is inadequate for punching shear. So, what we can do is we can increase the slab because it is quite off, right, from the demand. So, I am increasing it by another 2 inches or 50 millimeter. So, we can redo the calculations for 250 millimeter. Now, because I have increased the thickness of the slab, my self weight of the slab is going to increase. So, that is going to be 25 into 0.25, which is 6.25 kilonewton per meter square, and factored load is going to be 1.5 into dead load plus superimposed dead load plus live load, and if you do that you get 15.75 kilonewton per meter square, and factored shear is W times the tributary area that we have already done. The tributary area is 8 into 9 meter, that works out to be 1134 kilonewton. So, you can see that increasing the thickness of the slab increases the demand as well, right. So, that is the reason the slab, we try to keep not over design it, because the self weight also is going to increase. Then to take care of the unbalanced moment, then we increase the demand by 20%. So, the entire demand increases to 1361 kilonewton, right. Now, let us look at the capacities. As you can see, now effective depth increases from 160 to 200 millimeter. Now, the perimeter also is going to increase. The D is increasing, the perimeter is also going to increase, because critical perimeter is going to be column dimension plus D, right, on either side. So, D by 2 it adds to D. So, the perimeter also is going to increase, right. So, if you substitute in this, Vc works out to be 1095.9.3 kilonewton, 1100 we can say, but the demand is 1361. So, you can see that we are off by 260 kilonewton roughly, right. So, 260 kilonewton is what we are short of. So, now that I have increased to 250 millimeter, still the demand is higher. Now, I want to take advantage of the VP component, right. Initially conservatively we taken, but now still even after increasing the thickness to 250 millimeter, it is still not meeting the demand. So, let me see if I by adding VP still whether you are able to meet the requirement or not. Right. So, now we have studied in the previous load balancing approach as well, if the cable profile is parabolic, it is going to create a vertical force per unit length in proportional to the slope change of the cable profile. Now, the radial force, that is what we say here in this schematic, or can be derived as we have done in the previous classes as 8 into P into H2 divided by 2 beta L1 the whole square, because this entire length is beta L1 times 2, or in other words, so we can say that this is the overall length and this is your radial force equation. So, when you simplify that, that works out to be 2 into P into H2 by beta L1 the whole square. Now, H2 is the distance from the point of inflection to the top point of the reverse parabola, right, and beta L1 is basically from the point of inflection to the center where the apex of the parabola is situated, right. So, the total length over which that we are doing this calculation is 2 into beta L1. So, that is the reason in the denominator you have 2 beta L1 whole square, right. So, when you substitute that, you get this 2 PH2 divided by beta L1 the whole square, that is the vertical force per unit length that what we are putting because of the reverse parabola, right. So, this is the VP component. Now, I have to sum them up over the distances. Typically what we do is point of inflection, we try to keep it, this point of inflection in the cable profile, we will try to keep it close to tributary width. That is the reason beta 2 into beta L1 is equal to C1 plus D. So, this is C1 plus D is 2 into beta L1, because we try to keep the point of inflections close to that of your tributary width, right. It can be different as well, but in this case we are taking it like this. So, anyway, the vertical component of the pre-stressing is this. Now, when I multiply with the C1 plus D, then I am integrating. So, I get the entire VP. So, that is what we are doing. So, 2 PH2 by beta L1 the whole square is the vertical force per unit length. When I multiply that with C1 plus D, then I calculate the total vertical component of the pre-stressing force. Now, the effective pre-stressing force or the initial pre-stressing force, we take that as 0.75 times 1860, and area of the pre-stressing strand is 98.7 millimeter square. So, the maximum pre-stressing force is 1395 times 98.7. So, I apply 137.5 kilonewton, and beta L1, that is the reason I said it is going to be 350 millimeter. So, how do we get 350 millimeter? So, basically it is going to be 250 plus this is going to be 250 C1 by 2 plus D by 2, which is 200 by 2. So, that works out to be 350 millimeter. C1 plus D is nothing but 500 plus 200. So, you get 700 millimeter. So, these are the numbers, right. So, now when you integrate it, you get the total force, it works out to be 15.71 kilonewton for one particular cable. Now, if you look at this tributary area, that what it is here, right. So, you see here it is crossing number of cables 1, 2, 3, 4, here it is 5. Similarly, on the other side you have some cables as well. So, we are saying that how many on all the 4 sides we have to take care of this VP, right. So, that let us assume that the 10 tendons are crossing all the critical sections together in both the directions, then the overall VP will be 10 into 15.71. Of course, we have to verify that later, right. So, I am assuming that typically that is how it is, it is a good number. We do not know how many cables are there at this point of time, but because I am going to put banded tendons in one direction and uniform tendons in the other direction, and I am assuming that 10 tendons will be crossing that shear perimeter in both the directions, right. So that is the reason that we are saying that we are multiplying by 10 this Vp, and then I am getting the total vertical component is 157 kilonewtons. So now when you add them up, nearly they are working out to be okay. So we can still consider the slab thickness as 250 millimeter, and you don't want to be too far away, right. So if at all still there is a problem in terms of punching shear, then what I can do is I can go ahead and put a drop panel or a column capital at a later point of time, but not at this point of time. So we say that now the shear capacity and demand is nearly same. So we can go ahead and take 250 millimeter as the thickness for the slab. So next, now that we have come up with the thickness of the slab, the next thing is to how much we want to balance. As you have seen, the majority of the load that comes from the dead load. So we try to balance 80 to 100% of the sulphide for the economical design, so that if the superimposed loads are less than the sulphide of the slab. So that is a typically acceptable range. So we are taking here trying to balance 90% of the sulphide. Right. So now what is the philosophy for choosing the tendon profile? Typically in one direction we try to keep banded. You can keep both the directions also banded, but typically what we do is in the shorter direction or the shorter direction we try to keep a banded cable profile, on the other direction, which is in the east-west direction, we try to keep uniformly distributed cables, right. Now in the column regions, that is the reason. So we are going to place the tendons in the shorter direction of the structure, and below them there is of the longer direction. So now you can ask me, why do we do? Because in the shorter direction, now the tendon profiles have to come like this, right. So on one side it has to go, and the other side it has to, so you have to make sure that which cable profile you have to place below another one. So typically what we do is the longer direction should have higher eccentricity, so we try to keep it above, depending upon how you look at it, at the support direction, right. So that you maximize the eccentricity for the longer span. So that is the idea. So that is the reason the tendons in the shorter direction is kept below than those in the longer direction, right. Now the determination of the maximum eccentricities, let us look at now how much is the maximum eccentricities that are possible, right. Now this is what I said. So this is the tendon in the north-south direction, the red color ones are the flat duct that it is going when you are looking at it in the east-west direction. So you have to accordingly, you have to calculate what is the maximum eccentricity that is available. Now if I am assuming that 10 mm dia non-prestressed steel is also used as per the code recommendations. So you need to have some minimum bonded steel as per the code requirement. So we say that okay, I am going to have a 10 mm dia normal non-prestressed steel at the top and bottom of the slab for meeting the minimum requirement for the bonded reinforcement. If I do that, then again for the 2-hour fire rating as per IS 456, you need to have minimum clear cover of 25 millimeters. So with this, if you look at it in the east-west direction, again the cables are at the top. So the eccentricity, the available eccentricity is nothing but overall depth by 2, because this is a CG, right, minus 25 millimeter clear cover, minus the diameter of the bar, then minus the duct diameter divided by 2, which works out to be 80 millimeter. So 80 millimeter is the available eccentricity for the cable which is running in the east-west direction. Now for the north-south direction, again we have to subtract one more 20 millimeter, because the duct has to be subtracted. So again the duct, though you may use a HDPE duct or your metallic ducts, if it is grouted, still the PT cable will be at the center of the duct. So you have to subtract half of the duct size to get the effective cover. So that is what we are doing. So in the north-south direction, so you get 60 millimeters. So it has to be lesser than what you get for east-west direction, because in the north-south direction your spans are lesser. So that is the reason we try to keep the north-south direction below the east-west direction, right. So, now at the midspan again 250 by 2 minus 25 minus 10 minus 20 by 2. So, again you work it out to be 80 millimeter is the available eccentricity, right. Okay. So, now let us look at what is the pre-stressing force that it is required, right. So, this is a typical interior span that we are taking, okay, and you can see that there is also going to be a reverse parabola that what we have shown. So, you are going to have this reverse parabola. So, if this cable is extending like this, it is going to go like this, right. Right. So, this distance, if the cable is extending, if there is not going to be any reverse parabola, then the distances between the reverse parabola actual cable profile and this is h2, right. Now, the point of inflection distance from the support, we take that as beta L, right. And as I told you, beta L, we try to keep it as the width of the shear per meter, which is going to be C1 by 2 plus D by 2, which is 500 by 2 plus 200 by 2, which is 350 millimeter. And H2 from the equations of your reverse parabola and parabola, previously we have calculated that H2 is working out to be beta L by alpha L times E1 plus E2, and beta L we calculated to be 350 millimeter. Now, what is alpha L? Alpha L is the half of your span for the east-west direction. So, it is going to be 4000. So, you get this 4000. So, you get your E as E1 plus E2 plus H2, which is working out to be 174 millimeter, right, and P into E. Now, that we got the eccentricity, we can find out, now what is that we have said, 90% of dead load has to be balanced. Okay. So, now what is the dead load? Dead load is unit weight multiplied by 0.25 times L square, which is span square, divided by 8. Okay. So, now this is basically P into, sorry, this multiplied by 0.9. So, this should be equal to P into E should be equal to 0.9 times this, right. So, that is what we are doing. P into eccentricity, which is 174 millimeter, should balance 90% of the self weight. So, if you back calculate, I need 258.6 kilonewton per meter, right. That is the pre-stressing force that is required for the east-west direction to balance 90% of your dead load, right. Again, this is the picture that tells you, why did we do this, you can see here the cable profile. There is this always, it's going to go like this and come and then come. There is going to be a change in, so the cable profile cannot abruptly change. So, that is how there is always going to be a reverse parabola over the column support, right. So, just to really say, and you can see that one side you have, another side you have cable profile going in this direction, right. So, this side and this side you have cross. Okay. Now, let us calculate what is the, in the end span, what is the pre-stressing that is required, right. So, we do the same calculation like what we have done, beta L still remains 350 millimeter, and H2 in this case slightly it is going to change as per our equation. So, E1 plus E2. So, E1 and E2 are, I am trying to keep the same. So, 80 plus 80, because this is in end span, what is happening? So, here your eccentricity E is equal to 0. So, here you have eccentricity and here. So, the cable profile is changing. So, accordingly the equation for H2 is also going to change. So, if you substitute that, your H2 works out to be 10.77 millimeters. So, as you know, what is H2? So, again from here if the cable is extending, so whatever that is going, that is your H2 that what we are talking about. So, this distance is what H2 is what we are talking about, right. So, now that we got this H2, now what is the actual drape? Drape will be E1 plus E2 plus H2 by 2, which is 80 plus. So, this drape is basically, drape is you are measuring from here to all the way to this. So, this slope, this distance is going to be E1 plus E2 plus H2 by 2, right. So, this is the total drape that we are talking about. Okay. So, if you substitute that, the drape is 125.38 millimeter, and again what we are saying, 90% of the dead load for this span also has to be balanced. So, P into eccentricity, which is 0.125, should be equal to 0.9 into 25 into 0.25 into L square by 8. So, that works out to be, for this span, now I need 360 kilonewton per meter, right. For N span I need this much, and previously if you go back I got 258. So, we have to always choose a higher value, and in the interior span slightly I can adjust the eccentricity. So, I have to choose a higher value and then I have to design for it, right. So, now we have seen the pre-stressing force required in the east-west direction should be at least 360 kilonewton per meter. Please note that we are doing the calculation for a meter. Now, we have to find out how many number of cables that are required. We continue the same process now for the north-south direction in the N span, right. So, again we go and do the calculation and we find out what is H2. Now, again in the N span, here the eccentricity is 0. So, the drape will be equal to E1 plus E2 plus H2 by 2, and H2 beta L by alpha L times E1 plus E2. You plug in the numbers. So, that works out to be, this is 5850 here, right, for the N span. So, if you substitute that, you get H2 as 8.37 and eccentricity as 114.19 millimeter. Again 90% of the dead load has to be balanced. So, you find in the north-south direction I need more, because my eccentricity allowable is less. I need to put more pre-stressing, which roughly works out to be 500 kilonewton per meter. We do the same calculation now for the interior span. So, as you can see, you can now find out what is H2. So, this is the same thing. So, desired to use the same tendon force for exterior and exterior span. So, the eccentricity for this will be back calculated. So, that is the point. So, H2 we have already calculated as 8.37. So, E1 we have previously kept. So, E1 is what we are trying to find. So, in the interior span, what we are trying to say is, anyway that previous one will control this 500. For this 500, we are trying to find out what should be the eccentricity E1. So, that we can calculate it as 45.82 millimeter.